Welcome everyone. For today's prep, we're going to start to look at another way to test whether a series is convergent or divergent, and this one's called the integral test. So let's look at the statement of what this test actually says. Now this one has a little bit more going on, but it's called the integral test, and the idea behind it is it relates the convergence of an improper integral or divergence of an improper integral to an infinite series. So let's read through this. Suppose an is a sequence, and this is the sequence, the list of terms that we're trying to add all the terms together. And we have a formula for it. So we have a nice formula for a formula that generates the terms of our sequence. And this formula, this function, we have some very specific conditions here that we have to just kind of check. The function has to be continuous. The function has to be positive, so it has to be greater than or equal to 0. And it has to be a decreasing function, so it has to be sloped down. And it has to do this all on the interval from 1 to infinity. So first of all, why the interval 1 to infinity? Well, when we're dealing with a series, normally we're starting at index 1, and we're just adding all the terms up, going to infinity. So we kind of do the same thing with our improper integral. And as usual, we'll kind of see that we can relax this starting index. So sometimes we might have a starting index of 2, and then we'll just do a improper integral from 2, but we'll get there. All right, so what does this test say? Well, if we calculate the improper integral of that function, and we see that we get a value, it's convergent, then the series itself is convergent. And if we calculate that improper integral and we get that it's divergent, so we get that the limit doesn't exist, well then the series is divergent as well. So when we employ this test, there's a few things we have to do. So we first have to state the function. So the idea is we're taking our terms of our sequence an and we want to produce a real variable function. So basically what we're going to do is just change the n's to x's to get a real variable function. So remember, n is kind of the discrete case where we have just specific integers, and when we deal with improper integrals and calculus here, we want real numbers. So we're going to change any of the n variables to x variables. Then once we've stated our function, then we have to check the necessary conditions. So as we're going to see in a lot of these these series tests, there's kind of specific conditions that have to be first satisfied before we can even go on and perform the actual work of the test. So in this case, we have to go through our necessary conditions. And what are they? There's 3 of them. So we need to check that f is continuous on the interval 1 to infinity. We have to check that f is positive on that interval. And then we also have to check that f is decreasing on that interval as well. So if all 3 of those things are satisfied, then the next step is to do the improper integral. Calculate the improper integral. So we're calculating this integral from 1 to infinity of our real variable function f of x, and then kind of the last part of this is state the conclusion. So easy thing to forget there. All right, so we're going to try this out. Now one thing kind of seems obvious, but it's not always obvious when we're kind of dealing with more complicated series and sequences, is in order to use this test, you actually have to be able to integrate and find the antiderivative of f of x. So just a thing to keep in mind, if you have a really crazy looking formula for your sequence and the series ultimately, well, you might not be able to find the antiderivative. So just to keep in mind, you have to, in order to do this test, you have to be able to find the antiderivative. So sometimes that's easier said than done. One other thing to keep in mind is we're going to be calculating an improper integral, and sometimes we'll see that we'll get an actual number. That number is not usually the same thing as the sum of our series. So it's tempting, but usually what happens, we calculate this improper integral, we'll get a number. It tells us the improper integral is convergent, and then ultimately the series is convergent, but usually the sum here does not actually equal the value of our improper integral. So just one little thing to keep in mind. All right, so these hypotheses, these necessary conditions, we got to be a little careful. Sometimes, a lot of cases, they're going to be obvious. But it is something we have to keep in mind. So we have to check that our function's continuous. And usually the biggest thing here is you just want to look out for division by zero. That's usually where we run into the problems. Division by zero potentially produces a discontinuity. Or it does produce a discontinuity. All right, f being positive, it's another thing we have to check for. Is the function greater, is the output of our function greater than or equal to 0? And then the one that does sometimes take a little bit of work. These first two are normally just kind of looking at the function and just visually checking, does everything look positive? No division by 0, all good. Sometimes, though, it's not as obvious, though, is to check if the function's decreasing. And there's a few ways we can do this. So you can check it directly using inequalities. So you can suppose that you have two x values, one smaller than the other. And if your function's decreasing, when you plug them in, it reverses the order of the inequality. So if x1 is less than x2, when you plug them into a decreasing function, the output f of x1 is going to be bigger than the output f of x2. So the value's gone down. So you can think of that reverses the inequality. That's what a decreasing function does. Another way to check decreasing, and we did this back in Calc 1, is f is decreasing if f prime is negative. So another way to check f prime negative implies f decreasing. So all that business with sign charts and figuring out where f prime is equal to 0 and then splitting up the x-axis, well, we could do that here as well and show that f prime is negative, which means our function's decreasing. And then sometimes there will be cases where the function is just obviously decreasing. So we'll add a third one here. And we'll say it's obviously decreasing. All right, so what would that involve? Well, the cases are all the x terms that you see are in the denominator. And there's no subtraction of x terms. So kind of need both of those two things. So if you see you have a fraction and all of the x terms show up in the denominator and there's really no subtraction going on, well, then you're going to have a decreasing function. So these types of this test in particular tends to be a lot of work, even without going through and rigorously checking all three of these conditions. So there will be cases where it'll obviously be decreasing. And that's the first example we're going to look at. So Let's try out the test and probably look at the proof in class. So the proof, the idea behind the proof is we can think of our series essentially as a whole bunch of little rectangles, kind of like a Riemann sum that we're trying to do. And in the conversion case, we can fit those rectangles underneath our function, and in the divergent case, we can fit them slightly above our curve. And we need those conditions, those hypotheses, in order to ensure that in the divergent case, the rectangles are all sitting a little bit above, and in the convergent case, they're all sitting below. Okay. Well, let's actually try an example here, just to get a little practice. So we're going to look at this p-series, the sum from n equals 1 to infinity, 1 over n squared. So this is a p-series. The p-value here is 2. So we already know this is going to be a convergent p-series. But let's actually prove it using the integral test. So first thing we want to do, state the function. So what function are we going to be working with here? Well, it's not going to be 1 over n squared. It's going to be, we're going to convert it to a real variable function. And call it f of x. And it's going to be 1 over x squared. All right, so now we want to just double check. Does this function satisfy the necessary conditions? So that's step 2. We want to go through and just look at those necessary conditions. And when you're doing these, this is what we want to see. So state the real variable function and then check the necessary conditions, or state the necessary conditions. So first thing, f is continuous on this interval 1 to infinity. So where does this function have division by 0? It does have division by 0. So this function does have a discontinuity, but the only place it has division by 0 is when the denominator is 0. So when x is 0 here. And that falls outside of this interval. So we're good. Check. It is continuous on that interval. Now what about positive? Is f positive on that interval? Well, yeah. Why? If we look at the function, we've got positive 1, and then we're dividing by x squared, and x squared is always positive. So, check. Positive. We got one more. Decreasing. Third condition in order for this integral test to work out for us. And that is f has to be decreasing. I guess it would help if I could spell it. Decreasing on the interval 1 to infinity. And this is one of those cases where I would consider this obviously decreasing. So all of the x terms appear in the denominator, and there's no subtraction going on. So, yup, decreasing. Now, if you wanted to, you could prove this. So you could calculate the derivative. And what would the derivative be? Well, if we think of this as a negative exponent, we'd bring down the negative 2, keep x, subtract 1, and then if we kind of rewrite that as a fraction, we see that in our derivative here, we've got a negative on the top, and then we're looking at x values that are inside this interval 1 to infinity, so we're cubing positive x values, so that x cubed is always going to be positive. So we've got a negative divided by a positive, and the result here is always going to be negative. So f prime negative implies the original function f is decreasing. So if you weren't convinced, hopefully you are now. All right, so now we've stated our real variable function. We've got our necessary conditions. Now we get to the fun part. So this is all kind of the bookkeeping stuff. Now we actually get to the improper integral portion. All right, so we're going to calculate the integral from 1 to infinity of 1 over x squared. So our real variable function here. So for an improper integral, first step, rewrite this as a limit. So we're going to peel the infinity off of the integral sign, and we're going to replace it with some new variable b. So we'll do the limit as b goes to infinity, the integral from 1 to b. Same function, 1 over x squared. Okay, so we get our antiderivative. And again, if we use negative exponents, we add 1. So it's x raised to the negative 2. So add 1 to the exponent gives us x raised to the negative 1. Take that new exponent, flip it, put it in front. So we get 1 over negative 1 in front. And then we're going to evaluate this from x equals 1 to x equals b. Before we do the evaluation, let's clean up our antiderivative a little bit. So in this case, we're doing the limit as b goes to infinity of negative 1 over x. X equals 1 to x equals b. And let's do our evaluation. So top number gets plugged in first. Oops, no equal sign there. We get negative 1 over b, and then we subtract, and we plug in the 1, the lower bound. So we get negative 1 over 1. And if we calculate this limit, b is going to infinity. So this first fraction here, this is a c over infinity form. So that's going to go to 0. And we have a double negative here, so that becomes positive, and 1 over 1 is just 1. So this ends up being 0 plus 1, which is 1. So that's not our answer. But what this tells us is that the improper integral is convergent. Okay, so this improper integral is convergent. So now we get to actually state the main conclusion. We weren't really interested directly in the convergence or divergence of this improper integral. What we actually are interested in is the convergence or divergence of this infinite series. So this is convergent. And whenever we claim a series is convergent or divergent, you want to state what test you use. So in this case, we use the integral test. Okay. So the difficult thing about this test is, well, there's a lot of baggage here that you have to check first of all. And then sometimes for a series, you might not be able to actually find the antiderivative of the function that you have. So we're going to be looking through a whole bunch of different series tests, and it'll kind of be just a whole tool bag of different ones to use at different times. So sometimes there'll be cases where integral tests will work, sometimes it won't. So we're just going to get a little bit of practice with all these different tests. All right, so we'll keep going in class. We'll see you then. Bye-bye.